Okay, so in class we went over the pre-lab assignment just very briefly about what we'll be doing for our lab, finding how many moles of water are trapped inside a hydrate. So what we have here is a very similar question that outlines the same experiment that we will be doing, just a different compound. So question number 1 says, in the first 2 experiments, a student is assigned the task of determining the number of moles of water in 1 mole of magnesium chloride something hydrate. So we want to figure out how many moles of water in 1 mole of magnesium chloride something hydrate. The student collects the data shown in the following table. So here's the mass of the empty container. So tomorrow you will have a crucible or an evaporating dish and you'll take the mass of that. In this, you will take your sample, which is some kind of hydrate, and you'll place it in your container and then reweigh it. The reason why we are weighing the container each time is because we don't want to dump out our sample, re-put it in, dump out our sample, re-put it in. So that's why we're going to keep the mass of our container. So in this container, we have our hydrate. So this is the magnesium chloride something hydrate. And then we're going to heat it. And when we heat it, we release all those water molecules into the atmosphere. And after so many heatings, we try to figure out when does the mass stay constant. When it stays constant, that must mean that we have sufficiently taken out all of the water from the hydrate, and now it's all gas vapor, and this is just what's called the anhydrate. So just magnesium chloride without any water trapped inside. So the first question says, explain why a student can correctly conclude that the hydrate was heated a sufficient number of times in the experiment. So looking at the first heating, he heated it up, took it off, let it cool, and then weighed it. He heated it up again, took it off, let it cool, then weighed it. It went down in mass, so it's losing water. And the third time he heated it up, let it cool, and weighed it, and you notice there's a change by 0.001. And this can be confusing. Once we have already removed all the water, sometimes the reaction will go backwards and start to absorb water again. So after we heated it and let it cool, it's almost as if it absorbs some more water. So you always want to choose your smaller amount, the lowest value, because that's the one that had the most amount of water driven off. So this one, we'll just say constant mass. They explained it verbally, but you should give me a little bit more detail in your answer. For part B, it says, use the above data to calculate the total number of moles of water lost when the sample was heated. So we know that we're starting out in the container with a mass that has some water trapped inside. And then we're heating it until the water is released. So if we compare these two values, we'll know how many grams of water was released from our system. So 25.825 grams is my hydrate with the container. And 23.976 grams is just my ionic compound, my anhydrate, what does not have water in it. So I got 1.849 grams of water driven off from this experiment. But the question asks how many moles. So most of us know how to do this. There's 18.02 grams of water in 1 mole. And I got 0.103 moles of water. All right, so we got A, we got B part 1. So now we just need to figure out the formula of the hydrated compound. So we know that during this experiment, 0.103 moles of water was completely released. But we need to compare that to how many moles of magnesium chloride we're starting with. For every 1 mole of magnesium chloride, we need to figure out how many moles of water was evaporated. We have 0.103 moles of water being evaporated. So how many moles of magnesium chloride are we starting with? Over here, this guy is just the container with your magnesium chloride that's without water. If we take the mass of the original container and subtract it by the mass of just your ionic compound, magnesium chloride, from the container, we'll figure out how many grams of magnesium chloride we have. So I'm going to write it up here. So 23.976 is the mass of magnesium chloride with the container, minus 22.347 is the mass of just the container. So we have 1.629 grams of just magnesium chloride in the compound. So now we can make some kind of comparison. If I know how many moles of magnesium chloride I have, I can figure out the ratio between moles of magnesium chloride and moles of water. So 1.629 grams of magnesium chloride to moles, I would have to find the molar mass, which is 95.2 grams. I've already calculated that. And I got 0.017 moles of magnesium chloride. So I know for every 0.017 moles of magnesium chloride, I'm going to get 0.103 moles of water driven off. I just need to be able to write this into a chemical compound. And the question asks, determine the number of moles of water in 1 mole of magnesium chloride. So you can write it like a ratio. For every 1 mole of magnesium chloride, how many moles of water will be in it? Because we know for every 0.017 moles of magnesium chloride, you get 0.103 moles of water. Simply cross multiply and divide. Oh, I'm running out of room. And you'll find for every 1 mole magnesium chloride, this X here is approximately 6. Oop, running out. So your chemical formula is MgCl2, magnesium chloride, times 6 waters. Magnesium chloride hexahydrate is your chemical formula. All right, let's do the next problem. So part C of the problem says a different student heats up the hydrate in an uncovered crucible, and some of the solid splatters out of the crucible. This splattering will have the effect on the calculated mass of water. This splattering will have what effect on the calculated mass of water lost by the hydrate, and justify your answer. Okay, so if we look at our data table, we notice that we are really concerned about the mass being lost, and we are assuming that it's all water. If we make that assumption and more mass is being lost, then we'll record more moles of water being lost. And if more moles of water are being lost, then we're going to have a different ratio in our chemical formula. Let's say twice the amount of moles are being lost. Then this chemical formula would really be magnesium chloride with 12 waters instead of 6. So if some of your sample splashes out, you might think that it's water. You might record it thinking it's water, and therefore the formula of your hydrate would be too large. You'd have too many moles of water in your chemical formula. Okay. Next is a kind of unrelated question, but we'll be doing it in our lab for the 2-day, 3-day lab, depending on how many days it takes us to get it done. Brand new question. It says, in a second experiment, a student is giving 2.94 grams of a mixture containing anhydrous magnesium chloride, so without water, so it's not the same thing we're dealing with, and potassium nitrate. To determine the percentage by mass of magnesium chloride in the mixture, a student uses excess silver nitrate solution, aqueous, to precipitate out the chloride ions as silver chloride. So just as a reminder, we have this mixture of magnesium ions and potassium nitrate ions. And a student dumps in some silver nitrate, and we get this double replacement reaction we get silver nitrate plus this magnesium chloride making silver chloride plus magnesium nitrate. Using the solubility rules we got from honors chemistry, you would have to determine which one is the precipitate. And they already tell you that silver chloride is the precipitate. So, in all of this silver chloride, the chlorine atoms only came from the magnesium chloride. So if we can figure out what mass and what moles of chlorine are in this precipitate, then we can figure out how much magnesium chloride we started with. So the question says, starting with a 2.9 gram sample of the mixture dissolved in water, briefly describe the steps necessary to quantitatively determine the mass of silver chloride in the precipitate. Okay, so you want to make sure that you're starting off with a solution. So you have that 2.95 grams in water, perfect. Double replacement reactions will not happen unless they're in solution. Next, you're going to pour silver nitrate until all precipitation. So you want to make sure you keep pouring silver nitrate until you have no more formation of solid. Once you do that, you want to find a way to separate the solid from the solution. So maybe you can pour it over a filter. Pour mixture over a filter. When you pour it over a filter, it'll catch all the solid, it'll catch the AgCl, the silver nitrate, and all of your other ions will go straight through the filter because it's in solution. It's kind of like coffee grounds. You want to dry the filter paper and weigh your sample. You don't want to weigh a wet filter paper because it's going to be heavier with all the water. So you want to make sure it's dry. And now thinking about this, if we are weighing our filter paper with our sample in it, we probably should have weighed our filter paper somewhere before. So let's say weigh filter paper maybe up here as a pre-step. That way you know what mass is the filter paper and what mass is your actual sample. There are more details that go into this, but this is the general outline, and we're going to spend a day going over the details of this type of procedure, but I want you to visualize the basic steps, and we'll talk about the nitty-gritty details later. But let's continue with the question. It says the student determines the mass of silver nitrate precipitate to be 5.48 grams. On the basis of this information, calculate each of the following: the number of moles of magnesium chloride in the original mixture and the percent by mass of magnesium chloride in the original mixture. We will be doing these two steps when we're trying to find out how much copper is in brass. So let's start with our balanced chemical equation that I wrote up here. I'll just rewrite it. If we're going to add silver nitrate solution to a magnesium chloride solution, you might be thinking, why am I not including this potassium nitrate? Why am I not putting potassium nitrate into this equation? Well, remember, if something forms no precipitate, it's no reaction for a double replacement reaction. Nitrates make everything soluble. There are no exceptions to that rule. So when nitrate, silver nitrate, and potassium nitrate come together, there's no precipitate. So there's no need to write a balanced chemical equation for it because no reaction is happening. I'm only going to write a balanced chemical equation for the reaction that's actually happening. And that's when we make this solid here, silver chloride. And this is aqueous because nitrates are soluble. If you need a moment to look up your solubility rules, this is where all this information is coming from. From honors chemistry, when we did double replacement and single replacement reactions, solubility rules go with double replacement reactions. So the question tells us is that we have 5.48 grams of this precipitate. And the question asks how many moles are in the original mixture. Well, all the silver that came from silver chloride is coming straight from magnesium chloride. So this is just a stoichiometry problem. So in order to do any sorts of stoichiometry, you gotta start with grams and you've got to go to moles. So we have to find the molar mass. Silver weighs 107.87, and then chlorine weighs 35.45. So 143.32 is the molar mass. All right. For every 2 moles of silver chloride that is precipitated, we've only started with 1 mole of magnesium chloride. So for every 2 moles of silver chloride, we start with 1 mole of magnesium chloride. And that's it, moles of magnesium chloride. Okay, so 5.48 divided by 143.32 divided by 2 is 0.019. Let's do 91. Perfect. So that's how many moles of magnesium chloride we started in our sample. Now it says, what is the percent by mass of magnesium chloride in the original mixture? Well, the original mixture is a 2.94 gram sample. So my total mass is 2.94 grams of this mixture. I know how many moles I have, I just need to get that to grams. So 0.0191 moles magnesium chloride divided by the molar mass. So magnesium is 24.30 plus 2 chlorines gives me 95.2 grams per mole. Oop, made a mistake. Didn't cancel. Okay, let's try this again. 0.0191 moles of magnesium chloride. For every 1 mole of magnesium chloride, it weighs 95.2 grams. Okay, now let's try that. So I got 1.82. 1.81 grams. Well, 82 grams of magnesium chloride. So from my moles of magnesium chloride, this is the mass I got by just finding its molar mass. So if I only have 1.82 grams of magnesium chloride in my overall sample, this will tell me what percent of my compound is made up of magnesium chloride. Sorry, what percent of my mixture is made up of just magnesium chloride. So 1.82 divided by 2.94 gives me 61.9%. Okay, so question 1 is just like question 2. I ask you to do the exact same steps to find the hydrate. So you're going to have to clarify why this indicates that the reaction should stop, why you should stop heating after constant mass. You'll find the moles of water. You will find the formula of the hydrated compound by comparing the moles of water to the moles of the salt, the anhydrous compound. This one they ask you to find the molar mass of the hydrate. I think you guys can do that. I think I need to show you. And then the last question is like the question I just solved. You have a mixture, there's a precipitate that forms, and you're going to use the mass of that precipitate to find out how much of each component was in this mixture. Okay, that's it.